and then we'll go on to discuss other nonlinear non-idealities. So we have, just to recap, we have started with inverting amplifier, shown here. This is pretty similar to what you've done, treating it as an ideal op-amp. And then we went down to remove the restrictions that the gain is no longer infinite, and the output voltage is now equal to the open loop gain times V plus minus V minus, so the difference of the two terminals, and their voltages are no longer identical. They are very close, but they are no longer identical. And we went down using KCL, KVL, together with these output input characteristics of the op-amp. We have derived the new transfer function. So if you recall, this is the new transfer function that we have derived. And in addition to the same factor of the resistor ratio, R2 over R1, we have now these more precise correction factor, which is 1 plus these numerator divided by the open loop gain. Since the open loop gain is very large, it's not infinite, but I say, well, you can usually think of it as something like a million. In this case, the second term in the denominator does reduce to 0, and will reduce to the ideal op-amp behavior. Now, to understand the frequency dependence, then we substitute the constant gain, A, with the frequency dependent gain, and we just model with a single pole response of an op-amp. So this is a single pole response. We explained why there's a single pole response, kind of overview, simplified analysis of what is inside an op-amp. Why do we have this single pole response? And once you substitute that in, you'll get this new expression. We've done that last time, so I won't repeat it here. And again, you do some simplification, you'll find that we now have kind of a new pole frequency. So this term here represents the new pole frequency. If we ignore this term here, since it's divided by a very large number, A0, okay? Let me put A0 here. So this is the overall response of the circuit element superimposed on the raw response of the op-amp. So the blue line here is the op-amp, and the red line is the example of amplifier with inverting amplifier with the R2, R1 value here. So this numerical example, I guess we can kind of gain a little bit more insight. In this example here, A0 is 100 dB, okay? 100 dB, remember this is 20 log. So in linear scale, this is really 10 to the 5th. So I said, well, think a million. This is a kind of close to a million, 100,000, okay? And in this case, the R2 over R1, the gain of the inverting amplifier is roughly about, well, 30 dB, not exact, but let's say roughly about 30 dB. 30 dB in linear scale is 10 to the 1.5 times, okay? So this is about 30 also. Yeah, roughly. So now we have reduced the gain substantially from 100,000 to 30. At the same time, our bandwidth have gone up also substantially from 10 to roughly about this number. So the increase in the 3 dB frequency, so the new 3 dB frequency divided by FB. FB is the 3 dB frequency of the open loop gain. And we see that the bandwidth has been pushed out by this factor. So this is by the open loop gain and over R2 over R1, okay? We can read it out from basically here, okay? It is roughly 70 dB, okay? And this is about 10 to the 3.5 times. So that's roughly about 3,000, so 3 orders of magnitude. So it goes from 10 to 1 order of magnitude, 2 order, 3 orders of magnitude, and this is about 3. So this is about 3,000 times higher. So our bandwidth becomes 3,000 times higher. Our gain is about 3,000 times lower. The gain bandwidth product remains the same. And in fact, this slope here, this slope represents same gain bandwidth product. So anything that intersects with this line is the same gain bandwidth product. Okay. So as a different example, let's say, let me change your color to green. So let's do example 2. Example 2. Now I'll say, well, let's choose a different value. I now have a very large R2 over R1. Let's say now I have it just a 30 here, and I'll choose 1,000, just for example, to be more different, okay? And if you convert to dB, this will be 60 dB, right? 20 log, so that's a 60 dB. So my low frequency gain will now be here, all right? And what about my 3 dB frequency? My 3 dB frequency, we can do this again, A0 divided by R2 over R1. So this is 100 dB. I shouldn't do divide. In dB, they are actually subtraction. So this is 100 dB minus 60 dB. So this is 40 dB. Okay. 40 dB is in linear scale 100 times, right? Remember 20 log. So these bandwidths will be extended by 2 decades, all right? So I'll go up here and I'll go here. So now this green curve is the transfer curve of this example 2. And you see that it always meets in the same 20 dB per decade line. I can choose different resistor ratio. This gives me, as a circuit designer, a degree of freedom in tailoring my gain and bandwidth. But I'm limited by what the raw op-amp provided me. It has the same bandwidth product. I cannot go beyond that. I cannot, out from this op-amp, design something with 60 dB gain and the megahertz bandwidth. It's just not possible. Towards the end, we'll talk about how to do that, okay? Basically by choosing a higher bandwidth op-amp in a short answer. Okay, so that completes our discussion of the finite gain, finite bandwidth of the op-amp. Any questions so far? Through the discussions, we have utilized the concept of feedback. So this example of inverting amplifier is actually one special form of feedback. And we have presented a more general framework for feedback. Feedback basically gives us this trade-off, gain bandwidth trade-off. So that's exactly what the inverting amplifiers illustrate. Okay, no further questions. let's move on to the topic today. That is other nonlinearities of op-amp, okay? What are the other nonlinearities? We talk about all these golden rules which will not strictly be valid if we consider the finite gain, finite input resistance, and so on. There are other imperfections. These are mainly nonlinear imperfections. And this includes slew rate, finite swing, output swing, offset voltage, and the input bias current, noise distortion, and so on. So we're going to kind of, in a more brief discussions, kind of go through all these different limitations and what are the implications of these limitations. Okay, so let's start with the offset voltage. On the right is the transfer curve of a typical op-amp, and an ideal op-amp. Let me use green. Ideal op-amp will be something like a green line here. Okay, it actually passed through the origin. So this is ideal op-amp. That when there's no input voltage, here the x is VID. VID is equal to V plus minus V minus. So the difference of the voltage at the two input terminals. Ideally, when they are equal, there should not be any output voltage. However, this is an analog circuit. An analog circuit actually needs quite a bit of tuning and matching of the transistor. And towards the end, I'll tell you, you should be able to understand why there is offset voltage. In a simple view, in a nutshell, the main reason is this relies on perfect matching of transistors in the pair. So the input terminal and output terminal, the plus and minus terminal eventually goes to the input of a transistor. If these two transistors are identical, literally identical, then there's no offset voltage. In reality, even though they are same design, there are always some minute differences. These minute differences manifest itself as an offset voltage. So this is kind of representation to remind us that there exists a finite offset voltage. And the effect of the offset voltage is such that, the transfer curve are shifted to either right or left side. Could be, depends on the particular mismatch. Another thing to talk about this op-amp is, this slope is very, very steep. This slope is essentially, or now I guess in this real op-amp, this slope is basically equal to the open loop gain, A0. So I mentioned this could be on the order of 100,000 or a million. And if the output swing is 10 volts here, and the output vote is 10 volts, if it is 100,000, that means between the input, this range is really small. 100,000, 10 divided by 100,000, that's like 100, 10 divided by 10 to the 4/5, that's 10 to the minus 4. So only about 100 microvolt, your input range are allowed to vary. Okay, this has other implications. What happened when your input voltage difference exceeded 100 microvolts? Okay, there's another imperfections there. So, there is a solution to that, and this solution is basically external trimming. And if you look at the typical op-amp, they come in all shapes and forms. these are the two common packages that you are likely to see. One is a small DIP package, dual inline square IC. And you'll see there is inverting input. So this is a V minus. There's a non-inverting. So this is a V plus. And there is output voltage here. Okay. This V plus is a power supply voltage. They typically need two power supply voltage. So these are most positive power supply voltage. This is the most negative power supply voltage, okay? And here you will see two offset nodes. Two offset nodes, we typically will connect them to a potentiometer. And basically, you connect the two outer leads of a variable resistor to the potentiometer. And the center lead you connect to the most negative power supply. So these, for example, can be, if you use a 15 volt, this will be 15 volts. This will be minus 15 volts. So you connect that to the middle terminal. And you just physically tune. You short the input. And you take a screwdriver or hand, manually tune that until the output goes to 0. Okay. This can be automated somehow. You can have another kind of automatic circuits that do effectively this function. But if you use a discrete op-amp, that's effectively what you do. If you have a round package, that TOCAN, that's you see that pretty frequently also. It's a very similar arrangement. Okay. Yes? Question? What is the offset voltage? What causes it? So this will require us to look into what is inside of a transistor. Without kind of jumping too far ahead, you can think of the input stage be looking like something like this. Okay, without going through the details. Okay, so so here is V minus, here is V plus, and this is V power supply voltage. This is minus power supply voltage. And if these two resistors are identical, these two transistors are identical, then you expect the output voltage, which we take out from here, to be exactly 0. But imagine one of the resistor is off by 1%. That leads to unbalanced operation. And as a result, the output is not exactly 0 when it should be 0. And we will look at this circuit towards the end of the semester. Okay. All right. So now there is another non-ideality that is in practical op-amp. This op-amp applies to primarily bipolar junction transistor. So there are two types of transistor we will talk about. One is MOSFET. We will focus almost exclusively on MOSFET since about more than 90% of the circuit in use are MOSFET. Bipolar junction transistor are still popular, okay? And actually, your lab, you'll be using a bipolar junction transistor op-amp, okay? So that's called BJT, bipolar junction transistor in particularly, okay? The difference is bipolar junction transistor actually have some finite input current. So we say ideal op-amp, if you look in here, no current goes in here. Well, actually, it's not true. It takes finite current to bias BJT. And so usually two of them have similar amount of bias current, IB1 and IB2. IB1 are roughly the same as IB2, but just like the offset, they are not identical. So IB1 is roughly the same with IB2, but not identical. Okay. Let's see what are the effect of that. So let's say typically these are on the order of 100 nanoamp. So that's very small. Typical circuit operate at about microamp to milliamp, so nanoamp is really small. And they are not identical, so they are offset. The difference between them are typically about 10% of them. So this is about 10 nanoamp. Okay, 10 nanoamp, small but finite. What are the implications if you have this small current present? So let's look at, again, the same circuit we have looked at so far many times, inverting amplifier. So inverting amplifier, when there's no voltage, right? So for ideal inverting amplifier, when there's no voltage, VI is, well, let's say VI you apply here. Okay, let's say we apply VI here. When VI is 0, well, we expect VO to be 0, right? Now, if we now have the same 0 input, but we included this IB1 and IB2, well, what happened? The IB1 and IB2 now is different. These, let me get my notes up. This voltage is now no longer identical to 0. So why this is 0, but there is a finite voltage that flows through here. So there is a finite IB1. So if this is 0, this is 0 in assuming ideal amplifier. So this V minus terminal is 0 also. And there is a finite IB1 flowing. So the IB1 has to come from here. Because the other branch, there's no current because it's ground on one side, 0 on the other side. So all the current has to come from the output terminal. So you can now estimate IB1 is basically the DC offset VO divided by 0 divided by R2. So this means the DC offset of the voltage is IB1 times R2. Okay. And this could be significant, even though these are small. R2 could be significant, and to the point it is observable. Okay. These can be mitigated by circuit tricks. One of the well-known circuit tricks is adding a resistor R3 here. So this is the new thing. The difference between this and the previous circuit is simply adding an R3. Now, adding an R3 from a point of view of an ideal op-amp, it has no effect because if you ground here and there's no current flowing in, then this is still ground. It's still 0 volt, so it's identical. But in the presence of finite IB2, now actually the current flowing there is not 0. So IB2, so the current flowing through R3, this current is equal to IB2 because the input is draining that constant current. All right. So the voltage V plus is not 0 anymore. Okay. Let me do V plus here. V plus is not 0 anymore, but V plus is 0 minus IR drop, IB2 times R3. So in other words, it's minus IB2 times R3. What is R3? well, we will determine what is the best value of R3. That is to our benefit. Okay. So now VO is now equal to the voltage here. Okay, the voltage here is now minus IB2 times R3. So we're still using ideal op-amp characteristics. So these two voltages are the same, but we have an additional IR drop. So this has to be plus R2, okay, times IB2. Actually, the current, now there are current in both arms, so we have to be careful. So there is a current flowing through here as well, okay? And that current is 0 minus IB2 R3, okay, divided by R1. So that's this current flowing towards the terminal. And we have this current flowing down as well, okay? So we need to plus this is the current and minus. So we want to find the current through R2. Okay, so the current on R2, let me reverse this direction here. So it's this current minus IB1, okay. So this will be the current that will eventually go out this terminal here and times R2. So that's the voltage drop across this R2, and we get our V out, okay? And so to analyze this, we first let IB1 equal to IB2. So they are finite, but let's treat them the same first. And you're just basically arranging this circuit, this equation here. This equation will become VO equal to basically IB times R2 minus R3 times this factor 1 plus R2 over R1. Okay, it's just algebra. You can work out easily. So now look in this equation now, it's pretty inspiring. Is that, well, if you use, since we added R3, and R3 doesn't really change much of the functionality, so we can set R3 to be equal to R2 divided by 1 plus R2 over R1, right? And then VO will be equal to 0. So in other words, we have somehow mitigated this finite input current, okay? You can further optimize this. This is R1, R2 divided by R1 plus R2. You recognize this is simply the parallel combination of R1 and R2. So it's kind of interesting. You choose this new resistor equal to the parallel combination of R1 and R2. You largely cancel out the output voltage offset due to this finite current, okay? However, this is not the whole story. Remember, we set IB1 equal to IB2. Now, in reality, IB1 is like IB plus some kind of offset current, and IB2 is IB minus some kind of offset current, okay? The offset current is about 10% of the bias current. So now if you use these R3, okay, use these R3 value and use now these different IB, So you substitute these back into this equation, okay, back to this equation, and you'll find out, well, the dominant term cancels out, but with that, you'll find the output voltage to reduce to basically I offset times R2. Okay, so I offset is about 10% of IB. So we have reduced the impact by about 10 times. Okay, depends how well we can match these transistors. So it's not completely eliminated, but it's substantially reduced by an order of magnitude. These are the circuit tricks to mitigate the non-ideal characteristics of the op-amp. Questions here? So when you look for op-amp, there are two kinds of op-amp, and you need to look carefully. Some has input bias current, some doesn't. Okay. Output saturation. So output saturation, as we mentioned, the transfer curve of op-amp, if this is V out, this is V input difference, VID. It has a very steep slope here, okay? And then it basically rail means it just hit the power supply voltage with some small offset. You cannot go above power supply voltage. So if your input signal is very small, your input signal is basically just varying around the zero value, okay? And you can do your output. Your output will kind of follow your input. If the input is sinusoidal, you have sinusoidal varying at the output. Now, if your input starts to increase, if your input starts to be larger than this range here, then your output, you'll see, well, your output, ideally, your output want to go follow the input with a constant gain, but it runs into the cap, the rail, the power supply voltage. So your output is being kept here. So, you know, if your output is like that, and it has distortions now. So this is kind of illustrated at the diagram below here. Here, the 15 volt is power supply voltage, okay? You are not actually able to go exactly to 15 volts as we see the real amplifier circuit. You know, the circuit will take a cut. There are some headrooms that your transistors still have some finite voltage drop across them. So you're getting very close, but not exactly. In this example here, the 2 volts, there are 2 volts that are taken up by the internal circuit. So from the output terminal, you can go up to 13 volts here. In your circuit design, this is one of the parameters. Sometimes you'll try to optimize. You can optimize your circuit to say you have a minimum drop in this maximum swing. But this clipping basically creates a distortion. If you have a sinusoidal wave, if you hear it, if it is audio frequency, you hear a monotone sound. Our ears are not really very good, so we typically have instruments called spectrum analyzer. You'll see a single frequency at that particular tone. When you start to introduce clipping, well, you start to generate harmonic frequencies. So you start to create new frequencies that are not in the input. Remember, in the linear time invariant system, we said there's no new frequency generated. Whatever you put in, you get out exactly the same frequency. But with distortion, you start to introduce new frequency. this is equivalent of seeing illusion or ghost image. They are not really there in the input. They are there because of the nonlinear distortions of the amplifier that you use to pick up the signal. Okay, so this we hope to minimize. We hope to design it so that this never happens. Yes, question?
Isn't this mostly an issue of not having enough power, though?
This is an issue of not having enough power. You can say that. You say, well, what about I use, if I really want to go to 20 volts, I can use a 30-volt power supply. That solves the problem, but at the expense of increased power consumption. So yes, if we absolutely need to have 20 volts, we don't have much choice but to go in that direction. Or if we don't really need to have 20 volts, we need to work carefully designing our system to ensure our input never exceeded the range that will drive output into saturation. Okay. The next non-ideality that we need to live with is called slew rate. Slew rate is basically the finite rate that your output can respond. An intuitive version of this, you can think of voltage as like a water tank. Okay, if you have a water tank and the vertical water level is really your voltage, and you need to reach, for example, this VO, you need to reach this voltage. But your circuit is basically like a faucet. Okay, so you are really charging, you're really filling up the water. If you start from here, well, we all know it takes finite time to fill the tank. Your tank water level won't jump from a low level to high level instantaneously, but rather it will move over time instantaneously. So this is kind of illustrated here. Even though your input has a step response, so even your input has a step response, okay, your output will try to follow that. But this initial slope is just limited by the maximum output current that your voltage can supply. This is equivalent to you fully open your faucet, okay? That's just as much as water you can flow. And this is the minimum amount of time that it takes to reach the output level. So the steady state level is the same, okay? Steady state level is the same, but the transition, during the transition, you can say the transient part will be limited by the slew rate. So slew rate is defined as the output voltage, derivative of output voltage with respect to time, and the maximum value of that. That's called slew rate. And as you can check, the unit is volt divided by second. We typically use a volt over microsecond as a standard unit. That's more in the regime of operation. We typically are operating on microsecond time scale. So most of the data sheets listed as a volt per microsecond. 10 volt per microsecond is kind of a typical range. In 1 microsecond, the voltage goes up by 10 volts. It needs a lot of current drive capability to do that. Okay. Towards the end, we'll see a typical data sheet, and you'll see there are some op-amp that can exceed that. Any questions? Yes?
How would you increase that rate?
Well, basically by picking an op-amp that has a higher slew rate in the data sheet.
Well, like literally in the op-amp.
So towards the end, I'll show you. You literally have like 10,000 different op-amps you can choose. Some are designed for higher slew rate. If your application needs high slew rate, you pick those subcategories of op-amp chip ICs that have higher slew rate.
But if you're designing the op-amp and you want to...
if you are designing the op-amp, that is a good question. So if you go on to 140, you'll be designing a full op-amp, then yes, then you have to choose your transistors. You have to choose your transistor to be really at the output stage, really fat and big, so they have large drive capability. Their circuit tricks, certain circuit topology are more amenable to output the current very quickly. Yeah. So these people, these circuit designers, kind of labor through their design to produce a higher through rate. If we are simply users of IC, well, you just pick them. If you have an application that exceeded any of these available op-amp, you need to design your own op-amp. Then, yeah, you apply even more tricks to make that higher. Usually, high through rate comes at a cost. Circuit design is like engineering. There's no free lunch. So when you get high through rate, you usually suffer some setback in other specs. And you have to decide whether that's livable for you or not. Okay. Now, we previously talked about RC limit. Now, if your op-amp is driving some load that has an RC in there, okay, and there is a RC limit in the speed, okay, and both will limit how fast you reach the final voltage, but they are slightly different. A slew rate, you kind of go with, this is time domain, vertical axis is time here. You really reach to the final voltage at a constant rate. The slope is basically slew rate. Where if it is RC limited, this is RC limit. And RC limit, you know, these are exponential, okay? It approaches with an RC time. So this time here, when they cross the dotted line, this is actually the RC time. They generally have exponential behavior. This is this equation is 1 minus exponential minus t divided by RC. Okay, so they are slightly different. And if you look for them carefully, you can see them in oscilloscope trace. Now, if you are operating a real op-amp with slew rate limit in a load that it has RC limit, well, you need to determine one of them will be a dominant limiter. The dominant limiter, your rate will be slower of the two. If your RC rate is even lower than your slew rate, you're simply RC limited. If you are not RC limited, then you are limited by slew rate. So it's the lower of the two. There are some kind of signs. If you look at oscilloscope, if you have an input voltage, sinusoidal input voltage. So ideally, you have a sinusoidal output shown as this blue curve here. So ideally, this is ideal case. Now, if you see a distortion like this one, it's a typical signature of slew rate limit. The waveform departed from a sinusoidal waveform, okay? Here, for example, the slope, ideal slope, is too high. It's higher than your slew rate. So basically, you are chugged along with your slew rate here. Until you reach the desired output, well, the input has already changed the direction. So it's actually already coming down. And it's coming down, again, at a faster slope than your slew rate. So you just turn around and go backwards. So you ended up having a triangular wave, okay? This is the extreme case. Your slope here, your maximum slope is greater than slew rate, okay? Now, if you are kind of comparable, then you get a partial distortion. You don't get exactly triangular wave. In comparison, what would you see if it is purely RC limited output waveform? If it is purely RC limited waveform, let me reproduce this ideal output here. So your ideal output, it's hard to draw a sinusoidal, okay. So this is your ideal output, okay? And you are not slew rate limited, okay? Your output may be diminished. Remember the Bode plot, if you are over the RC limit, you are over the 3 dB bandwidth, your amplitude reduced, okay? So you get something like this. It's still a sinusoidal, okay? RC, as you know, in Bode plot, there's also a phase shift. So actually, you won't get that, but rather you'll get the offset. You get something like this in the time domain. This is what you can observe under oscilloscope, okay? So this is with phase shift. And the blue is with attenuation. This is with basically amplitude reduction. So by simply looking at it, you can tell what are you limited by, okay? And as a rule of thumb, we typically define a figure merit, a way for you to quickly check whether you are running into slew rate limit or not. So assuming, this is our ideal output, and we desire to have this VO, and we are operating at omega frequency, okay? If you take a time derivative, okay, sine become cosine, all right? And you have multiplying frequency here. And the maximum of this is basically when cosine omega t equal to 1. And this number should still be at most equal to your slew rate. So your maximum frequency times your maximum amplitude should at best equal to the slew rate. If you ensure when you are designing the whole circuit, you know what frequency you want to operate with, right? You know what is the output voltage you desire to generate. So if you multiply these two together, it's less than your slew rate, then you are fine. If you want to produce a guideline of what is the maximum full power bandwidth, then you divided omega, and you divided 2 pi and v over to the right-hand side. This gives you the maximum full power bandwidth, meaning beyond this frequency, you won't get full power. You'll start to be limited by slew rate. You won't get your full power. Okay, so this is basically a quick rule of thumb to check whether you will run into RC limit, slew rate limit or not. Questions? Yes?
What's the disadvantage of having a high slew rate?
The advantage of having high slew rate is you don't want your output waveform to be limited by your slew rate. Then you are not faithfully producing the input. So in terms of these very sensitive front-end analog circuits, it's all about fidelity. We talk about Wi-Fi. Wi-Fi came from hi-fi for audio. Hi-fi stands for high fidelity. So that's in essence all analog circuit design is high fidelity. If you pick up a signal, yes, you have a voltage, but it's not high fidelity of the original input. Well, you're more than picking up the signal. You are picking up distortions as well, and we try to minimize that.
And are you sacrificing anything if you're increasing your slew rate?
Yes, you always do. You always do. If you pick an op-amp with higher slew rate, yes, you always sacrifice something. And you have to look at the whole spec. There are generations of different technology. The very old op-amp, use older technology that may have higher capacitance, larger features. And, remember the first op-amp is designed in the 70s. So now it's almost 4 or 5 decades later. The technology has become a lot better. So certainly there are better technologies that can give you overall, just like gain bandwidth product, you can have overall higher gain bandwidth product. But there is still a physical limit. that will force you to do the trade-off. Any other question? Okay, so this is kind of what you look at. Your lab is quite straightforward. You're given an op-amp. It's one of the best op-amp that has existed for ages. It's a 741. It's actually a bipolar junction transistor op-amp. Just to illustrate how many op-amps are out there, nobody knows exactly how many different kinds of op-amp you can buy there. I picked from just one company, Texas Instruments. Texas Instruments is one of the two powerhouse now that produce a lot of analog circuits. The other one is called Analog Devices. There are many other smaller ones. They are gradually being gobbled up by these two giants. So if you go to TI's website, this link still works. You can click on it. And let me zoom up here for you to see. So you can pick for all the different parameters, number of channels. This is in an IC. How many op-amps are there? The one you have, maybe one, maybe two. You can get 4, sometimes 8. IC, the transistors are really small, so a big package, they can accommodate quite a few op-amps. So you pick how many you desire. You pick the power supply voltage. If you need to operate with 100 volts, you need to pick a op-amp that can sustain 100 volts power supply voltage. All op-amp has a spec for maximum power supply voltage. If you apply higher than that, you run the risk of killing the transistor, damaging the op-amp. So you pick one, let's say, okay, you want the range somewhere, this is the arbitrary selection. I say, okay, somewhere around minimum, around 40 volts, and maximum, I say, well, maybe I'm interested up to 100 volts, okay? So you down select all the ranges. The gain bandwidth product, so this is a figure of merit. We spend a lot of time discussing. I didn't choose anything, so I accept all gain bandwidth product here. You can choose slew rate, volt per microsecond. I didn't choose any, so I accept all possible slew rate. I basically have minimum choices in the first 3 parameters. Okay, and everything else, I just see what's all available out there. And how many did the TI's website pulls up? 1,468 op-amps. So if you want to go through all of them, it will take you a long time. So this means that you have to come back here, further narrowing down your spec. This is too many to choose. You don't know how to choose. Okay. But let's look again some of the results that it pulls up. Let's pick something of interest here. Let's say gain bandwidth product. Okay, gain bandwidth product. So this one I did not choose. And you can see gain bandwidth product in terms of megahertz. There are a lot of them in kind of the megahertz range. But here is kind of outlier. So this is gigahertz, 1,000 megahertz. So this one, and you look at the description, it's a high-speed closed loop buffer. So for an application that you need high-speed buffer, you pick this one. Every op-amp has a name suggesting how you use it for. Like this one, where it's a kind of mediocre gain bandwidth product. Why is it still in the catalog? Why would anybody use these op-amp rather than the very nice high-speed op-amp? Well, you get better noise characteristics. And if you're using it as an integrator, which is basically a low-pass filter, you most likely don't need a very high-speed response. And you can have low noise behavior. Okay, let me see if I have the noise. Okay, noise are not in this spec here, but if you go into the detail, you can see the noise. Let's pick slew rate here, for example. Okay, slew rate, volt per microsecond. Majority of them are between 1 to 10 volt per microsecond. And again, here is an outlier, okay, 8,000. So when you look at it, it's the same guy, high speed. Well, the high slew rate doesn't mean they really go to much higher voltage, but because they operate at 1,000 times faster frequency, your slew rate needs to be proportionally faster. Otherwise, you produce distortion at a much lower frequency, and that gain bandwidth product means nothing if your slew rate doesn't keep up with your application frequency and amplitude. So they kind of somehow always come hand in hand, and you can see kind of different combinations of those, right? So if you have time, you can just play around with these. You can go to analog devices. They will pull up different ones. You can put in all kinds of extreme conditions and see what you come up with. Okay, and you can compare that with the data sheet for the op-amp that you will use in the next lab. Okay, question?
Is there a reason the high-speed one is the cheapest of all?
I didn't look at the cost. Let's see. Is it the cheapest cost? On the right. These are, they are all very cheap. So this is like less than $1, $5, $21. These are all we price for 1,000 units. So this is when you buy 1,000 of them. Price are actually not, most of them are dated technologies. So these are usually produced in fully depreciated fab. What does it mean, fully depreciated? So if I build a fab, I spend $100 million, I build a fab. This $100 million is my cost, right? So I have to write it down every year. First year it depreciates 10%. That becomes my operating cost. I have to account it for. After 10 years, it's fully depreciated. So I have a fab that's still making a lot of functional ICs, but I don't have cost anymore. It's zero cost. I have already fully written it off, accounting-wise. I still have to pay people. I still have to pay operators. I still consume chemicals and supplies, but my costs are very, very low. Majority of these parts are produced in fab like that. They are fully depreciated. So the costs are all very low. The difference are likely due to the volume. If I produce a large number of these, they are and they are widely used, they are likely to be lower cost. If I produce something of a niche design, like some applications need particularly low noise, and I produce only a small number of them, the customers are also smaller, and the overhead is higher. It's not the physical production cost, it's just the overhead is higher, so the cost is higher. And just like consumer product, competition more likely to determine the price. You cut your price aggressively if your competitor, so there are two big competitors. If they have a much lower price, then you cut your price. So these prices are usually not reflecting cost. Okay. Any other questions? So this is the end of the discussions here. Let me also open it up, see whether you have general questions regarding the homework. If you have more specific questions, I have office hour immediately after class. One thing I do like to make a comment, we did not spend a lot of time talking about Bode plots because you have done a lot of exercise in 16AB. But let me remind you that there are many different forms of writing for Bode plots. We kind of emphasize the low-pass filters more, low-pass filter, okay? And it has a canonical form, at least that we adhere to in this class is 1 plus j omega over omega p. P represents pole, okay? And we say, well, this has the frequency response, actually 0 dB, so 0 dB. So, and the pole frequency, so here is omega p, and so on. All right. And if you have a low pass amplifier, okay, if you have a low pass amplifier, okay, now you have something like A0 1 plus J omega p, just like the op-amp we discussed. And well, it's a similar behavior that you shift the curve upwards. Okay, so now this is A in dB. You still have the same shape, same slope, 20 dB per decade. Both of them are, 20 dB per decade, right? And the phase response are very similar, right? We did not spend as much time talk about high-pass filters, okay? And high-pass filters is where kind of different people have different preference on the canonical form. And if you already kind of establish your habit in 16AB, don't change it. Just whatever works for you, just use it, okay? One form is 1 plus J, 1 plus omega, let me just say omega naught divided by J omega. Okay, this is not a typo. This is not the misprint. This is not the same as the low-pass filter. Well, what is it? Well, you can basically, whenever you are in doubt, just do a quick asymptotic analysis. So asymptotic analysis, I'll do, okay, when omega is much smaller than omega 0. So assuming omega 0 is still here, okay, and much smaller than this term, dominant, right? So the function, let's call this h of w. So h of w, let me do it here. H of w approaches, I'll drop 1. So this is 1, and omega 0 over J omega, okay, and this is equal to J omega over omega 0. So you'll see, well, this is actually a finite slope, okay, and the breakpoint is still here, so I will end up having something like this. This is proportional. This is proportional to omega, right? And I'll do another asymptotic behavior when omega is much greater than omega 0, and you'll see H omega approaches in this time, the second term drops out, so it approaches 1. 1 is equal to 0 dB, so my function becomes like this. So this is a high-pass filter, okay? And you can do one more asymptotic behavior. Say, well, omega equal omega 0, and at this time, H omega is equal to 1 plus J. So that's exactly minus 3 dB and minus 45 degrees. So this means minus 3 dB, and angle is equal to minus 45 degrees, okay? And so it's basically right at this point, 3 dB down. If you smoothly connect it, it's 3 dB down, okay? You don't have to solve what is 3 dB frequency. You look at the canonical form. It gives you your 3 dB response. Now, there are so many variations. I'm not even sure which version you learned or which version you practice. And some people coming from control courses, they will also have a different convention they use. I will not force you to use any fixed form. Just advise you to keep it the same every time you do it, okay? For example, another form, I just multiply J omega. So I can have J omega and J omega plus omega 0. This is kind of commonly used in control. People use S equal to J omega in textbook actually as well. So you have SS plus omega 0. That's a high-pass filter also. And again, you don't need to really solve it. If you kind of put it in this canonical form, you know this is that. Okay. Whether you use this form or this form, it's up to you. Just pick one and stick to it. Don't change back and forth. Then you won't confuse yourself. Okay. All right. There's no other question. We'll move on to the next module. Okay, last question, last opportunity for questions. Yes? Yes, okay, we can do that. So we say the OPAM kind of practical OPAM, real OPAM, it actually has a finite response. And finite response, actually we give you a rough idea, but we basically tell you in this ideal OPAM A, it becomes a finite bandwidth A. It's a single pole response. At low frequency, it's like our infinite bandwidth ideal OPAM, but we added the frequency dependence that its 3 dB frequency is omega B. So instead of having an OPAM that has infinite bandwidth in Bode plot, okay, we actually have a finite bandwidth that's omega B, and beyond omega B, it will start to go down with 20 dB per decade, standard of single pole response. So this is basically what we tell you at this level, at the current stage, that you can understand. We did go over what determines omega B. What is omega B? So what is omega B? We kind of give you a preview. Your OPAM really consists of two parts. Your OPAM, it's like we are sawing it apart. But realistically, if you are OPAM designer, you literally design the input stage called operational transconductance amplifier, OTA. It's in early part of this lecture. OTA is very similar to operational amplifier, but it's just the front input stage. It actually produces a current, not a voltage. It produces a current. So it produces a current, and the current is equal to some gain factor, transconductance gain, to the difference in voltage, or GM times VID, okay? We did not tell you how to design this. Towards the end, you'll kind of get an idea how to design that. And then in order to convert it to a voltage output, this is followed by a second stage that's like a unity gain buffer, okay? So this is like a buffer. It gives you drive capability. What do we mean by drive capability? It'll give you a low output resistance and large current and so on, okay? In these intermediate nodes, when you join these two together, there is a low resistor. So we say, well, there is an RX. RX is really the load resistance of OTA, okay, and plus the input resistance of buffer, okay. So you look right, you look left, all the input, all the impedance you added up together is RX, and there are unavoidable capacitance here, CX, okay. And these are the transistor capacitance. These are the wire linking these two stages together. They all have capacitances. So you end up having created an RC low-pass filter here. This RC low-pass filter end up giving you this low-pass response. Does that answer your question? Okay. Any other questions? Okay. If not, I'll just give you kind of a preview what we are going to discuss next. Next, we're going to look at material, semiconductor. What is a semiconductor? At the overview, we say silicon, and now silicon and germanium. These are really the magic materials that propelled us in the last 50 years for this amazing, seems endless Moore's law. So this magic material, semiconductor, what makes them magic? Why is it different from conductor? Why is it different from insulator? What particular property do we value? Okay, and what is a basic building block, a p-n junction? You know, you use diode a lot. You know, a diode, as you know, is a one-way device, current flow in one direction only. And you learn that when you apply 0.8 volts, the diode turns on. What does it mean, diode turns on? And as you go through here, you know, we have much finer granularity. We don't say diode turns on. The current kind of increase exponentially. What makes the current increase exponentially? What is this basic property of p-n junction? And this paved the road for our next module. Next module is what is a transistor? And how do we construct a transistor out from these basic p-n junctions? And after that, we get back to circuits, but much smaller circuits, like a single transistor circuit, rather than op-amp circuit, which is like roughly, you know, 30 to 50 transistors. Okay, we're almost out of time, so I think I'll just start next week. Okay, all right, thank you.